I will. Yeah, thank you. Yes, Professor Yellow Ted, thank you for your input. Professor Yellow Ted and he was just giving me final instructions so that I make sure I cover everything I need to in this very fine video. I will. I'll say that too. Goodness, I think Yellow Ted he's a bit demanding today, frankly. Anyway, today, class, pay attention. Cross your arms, fold your legs the other way around if you like. Stop throwing paper darts. Be quiet in the back. Attention. This is very, very important. Today, in as short a time as I can possibly muster, I'm going to cover Lorentz transformations, Minkowski Spacetime interactive diagrams, Relativity 101, Einsteinian relativity, and also the so-called twins paradox, which I'm going to resolve for you today. So let's crack on, shall we? Without too much further ado, what fun. All righty. So for those of you that aren't aware of it, Albert Einstein put together a thing called Theory of Relativity, which published in 1905, I believe, for the general formulation of it. What he suggested basically was that the geometry of space-time is, well, first of all, he suggested that space and time were two inextricably linked parts of the same fabric rather than two separate and immutable things. And he showed that, in fact, neither time nor space are fixed or immutable. They're both wibbly and wobbly and can stretch and compress in various ways. And there's a specific geometry to that being hyperbolic. Hyperbolic geometry. So what on earth am I talking about? Or indeed, what in deep space am I talking about? Let me show it to you graphically so that you can get some idea of what it is that I am on about. Let me just give you a little diagram here which will show you, I think, quite well what it is we are looking at. All right, here we go. No credit to me on this particular graphic there. That was put together by somebody else, and I've borrowed it from the interwebs. I think it's okay. Whatever, it's just two cones with a plane through it. Right, so what are these two cones? Well, the upward-facing cone, if you like, or the higher of the two cones on the screen as you look at it, represents your future light cone. Don't worry, I'll explain that in a minute. The bit below, the other cone, the one that's facing downwards, if you like, at its open end, the lower one, that represents your past light cone. Okay, what on earth is a light cone? Well, that's a diagrammatic representation of everything that you can see all around you, basically, going forward from this point in time. And the bit below is hypothetical, really, because it's gone, it's the past, it's finished. Time is only able to flow in one direction, that being inexorably forward. The only difference between one frame of reference and another is the rate at which it does that, according to Einsteinian relativity and according to this hyperbolic geometry of which we speak. What is this plane through it that draws these two hyperbolic curves that you can see on the chart there? Well, that's a way of displaying these cones in two dimensions, pretty much. So what it suggests is that if you move what's called your world line, which is the vertical line directly through the axis of both cones there, everything around that world line shifts hyperbolically to compensate for the fact that you've changed your world line. Okay, fine. I hear you say, or not. What is the world line? The world line is your, what's called your 4 vector, if you like. And it is your movement through space and through time. That's what we mean by space-time as an an inexorably linked fabric of a four-dimensional thing. I'll give you an example of it so that you can perhaps understand what I mean by that. If I said to you, Paul, I'll meet you at pub, what's the first question you're going to ask me? Great, Paul. When? Because otherwise there's no way we can meet. Or I might say to you, Paul, I'll meet you at 6 o'clock, to which you're going to say, fantastic, knob jockey. Where? So we need 3 dimensions of space and 1 of time so that we can meet at the same place, so that we can meet basically the same place and time, space-time. Okay, I'm glad we sorted that out. You have a 4-vector, and it is represented in the diagrams I'm going to show you soon as the vertical line through the middle of the diagram, and I'm going to show you a 2-dimensional diagram which you can interpret as a plane that you're looking at directly square on, which intersects exactly the point where the 2 apices of the 2 cones meet. Now, what is that point? That point is you right now. It represents your when-where. It's where you are and it's when you are. That's what that point represents. Okay, I hope that's as clear as mud. We don't want to waste too much time, so let's move forward. If you're struggling with that, comment under the video, flip me an email or something, and I'll try and explain it to you a bit more accessibly. But there you go. Lovely cones, aren't they, over there? Let's get rid of those, and we'll look at something a bit more user-friendly, perhaps. Okay, so let's go and have a look at a thing called an interactive Minkowski diagram. This is one that exists on the interwebs, which you can go to. I'll link the URL under this video so that you can find it for yourselves if you want to go and have a play with it afterwards, just for fun. And it shows that 2-dimensional plane directly through the meeting point of the 2 apices of those cones. So let's have a look at it, shall we? Here we go. Alrighty, there it is, an interactive Minkowski diagram. These things are great fun. The red dot there in the middle is the point between the 2 cones. The light cones are drawn with 45-degree sloping boundaries, if you like, or surfaces of the cones. Obviously, this is a section through the cones right through the middle, so all you can see is the grey lines here, which I'll highlight by mousing over them. There's one, and there's the other one. Everything below this horizontal axis here is the past. That which has occurred, that which is gone. Okay. Everything above that is your future light cone, which is shown in 2 dimensions here. The left-right dimensionality, left to right, that represents the length of your 3-vector in space, your movement in space, or the movement of something in space, I guess. A distance, really, is what it represents. What distance is it per square? The distance per square here, nominally for a scale, is 1 light year. 1 light year. The exact distance, 1 light year. That is what is shown left to right on each of those small squares. As you progress upwards in the upwards style here, that represents a period of time. That period of time being 1 year, as you perceive it to be. Because everybody's clock, as we'll see in a bit, runs at a slightly different speed. We'll come back to this diagram in a bit so that we can play with it and I can show you some really neat stuff. But in the meantime, let me just run over with you some laws that you will need to understand, which have been set down by Einstein. He didn't write these, I don't think, in these words himself. I think these are laws that are derived from his mathematical description of the hyperbolic nature of the geometry of the universe. There are 4 of these laws. They're called laws because a law is underpinned by a mathematical relationship between 2 variables, which is borne out by observation empirically every time. It is a law because it is inviolate. It has been tested. Every single experiment that has ever been done by any scientist anywhere on the planet to test whether or not this hyperbolic geometry idea is correct has borne it out and has agreed and has said, yes, it is correct. So these laws, there are 4 of them, are laws that I don't want you to second guess. I don't want you to question them necessarily. You can if you like, but that will make no difference. They are inviolate. These are laws for you to suck up. Okay, so let me provide those for you so that you might be able to so sucketh. Okie dokie. Here is law number 1. Relativity, rule or law number 1. There are no absolute frames. We're talking about inertial frames here. We're talking about how 2 bodies would view the universe around them. Okay? You have a frame of reference. I have a frame of reference. In terms of our inertial frame of reference, if we both sit somewhere on the surface of the Earth, then we will share pretty much the same frame of reference, and we will pretty much agree with each other with respect to the passage of time, the rate at which it occurs, and also the length of objects and distances in space. We will agree on that stuff pretty much within a degree of error so small that we will just say, yes, we absolutely agree. Okay. If you and I are sitting on completely different planets or at distances separated by a significant amount of time, distances separated by a significant amount of distance, for goodness sake, then we will not agree on the passage of time, the timing of events. I might say, yes, that was simultaneous. You might say, nope, no, it wasn't. One thing happened before another, because we are viewing time at a different angle, at a different rate. We will not agree on the length of things or the distances between things. And so that's what this Minkowski diagram is about. We'll get to it in a bit. All right. There are no absolute frames. There's no universal truth. This is the true frame of reference. Okay. Everybody's individual frame of reference is their own objective reality, is their truth. And they will not agree with each other. And yours is right and mine is right too. If we're on different planets, that is also true, but we won't agree on time or space, which is a bit disconcerting, really, until you work out how to do Minkowski calculations to work out something that we can agree upon. Okay. Given that there is no absolute frame of reference, there is no wire framework that the universe sits within that has absolute coordinates that we can refer to, there are no preferences between frames. No one frame is correct or incorrect. They're all correct. Well, your frame is correct and every other frame is incorrect in your understanding of it until you can do Minkowski. And everybody else's is correct in their own and everybody else's is wrong in theirs. So, okay, there we go. That's rule number 1. Suck it up. All right. Rule number 2 pretty much stems from rule number 1, and I don't think it's hugely different from rule number 1, but there you go. I think I've already said it. Every individual carries with them in their frame of reference their own Minkowski diagram, like I'm looking at here, over there. And like you're looking at too, if you're paying attention. Everybody has their own clock. So the rate at which time goes past for everybody is also different, and it depends actually on your movement through space. The more you move through space, the the less basically you move through time. Pretty much move faster in space, the clock ticks slower with respect to somebody else who's not moving as fast as you are. We'll get to it. Okay, so that's rule number 2. Now, of course, we need to go to rule number 4. I know. I forgot 3, didn't I? I can't count. No, I didn't forget 3. The problem here is most people do forget rule 3, and that's what this video is about. So I'll leave it out until it's very clear as to its relevance. That's why I'm skipping to 4. I know. There's a rule 3. We'll get to it. Anyway, here it is. Rule 4. A non-accelerating body in space will not experience motion. In other words, in your frame of reference, you are not moving. You are not moving with respect to you. Everything else around you is moving with respect to you. You are the center of your universe. I am the center of my universe. Everything else moves around me. Everything else in your perception of the universe moves around you. Example, let's say you are sitting on a train at the platform waiting for your train to depart on your way home from work, say, and suddenly in your peripheral vision, you see the people sitting on the train next door start to move with respect to you, which your brain immediately interprets as your train is moving, until you realize, hang on, you're not feeling any motion, you're not feeling any acceleration, you're not moving with respect to yourself, and there's no clues that you're moving with respect to something else, say the Earth. But nonetheless, for that split second, your senses are fooled and you think your train is moving. It's an equivalence principle here, okay? It's not until you double check and you look out the window, whoops, no, my train is not moving with respect to the platform. There are people walking on the platform still. They're not moving with respect to me. The other train is moving. That's what you see from your frame of reference in the universe. The only clues that we get are things like changes in momentum, acceleration, deceleration, moving around. Oh, now my train is moving. Okay, so I hope that's as clear as it can be. It's the principle of equivalence if you want to look that up for a better explanation than that. Okay, so there are rules 1, 2, and 4. We'll get back to rule number 3, but let's now go back and play a bit more with this Minkowski diagram so that you can see what it is that it does and how much fun it is. Jolly hockey sticks. Let's do that. Alrighty then. I'll just get rid of that so we can see what we're doing a bit more better. All right, here is a Minkowski diagram. So the 90-degree section here above the blue axis there through the point where you are right now, that is your future light cone. That is everything that you can perceive in the universe. Okay? This area here and this area here are both areas where things can physically exist, but they cannot interact with your reality because they are simply too far away from you in space-time. I'll give you an example. Let's say you are here, because you are. Let's move this dot across 1 light year in space from where it was. Okay? Now, tell me, please, how it is you can travel a distance equal to 1 light year, which is a sodding long way, to be fair, and you can achieve that while passing through exactly no time, the vertical axis. You can't. Teleportation is impossible. The fastest that anything can move that has mass in the universe is slightly slower than the speed of light. The only thing that can travel at the speed of light is light, or indeed something with no mass. Okay? So, would it be possible for a photon of light to reach you from 1 light year away, given 1 year to achieve that task? Yes. That's why that is in your light cone. If you, with a thing traveling, you have some mass, and so therefore the fastest you can possibly move is 0.999999999 of the speed of light, because mass provides inertia. Inertia provides mass, actually, and inertia slows you down in space. That's what it is. So that body, that person there, can interact with you here at 0, 0, 0, 0, so long as you are happy to wait for the best part of a year for that interaction to take place, for that person to move from there to there. I hope that is clear. Now, on this diagram, we can already discount everything below this line here, the horizontal line through the middle of 0, 0, because that stuff's all past. It's not accessible. You can't get to it. Doesn't matter in the instance of what we're talking about here in practical terms. Furthermore, this particular interactive Minkowski diagram only allows the warping of space-time from the orthogonal square version that we can see right now to a different version, and it can only slant one direction. The slider bar that slants the thing should be able to go both directions, so that we can go left or right. What that would indicate is that you have two directions in space, left or right. Okay. That is useful when you have a three-body problem. We're not dealing with a three-body problem today. We are dealing with a two-body problem, and such we only need one spatial scalar. It's not a vector anymore, it's a scalar. So in other words, what I'm doing is I'm collapsing down two of the three physical dimensions X, Y, and Z in space, and we are considering only the length of that vector, and therefore it is a scalar. And so everything that we're talking about here is only relevant to the right, as we look at it, of this vertical line that goes through 0, 0. So you can black out the whole left-hand side of the chart. You can also black out everything below right now, because that's already happened. So actually everything that's relevant is only relevant here in this top right-hand quadrant of the diagram. I hope that is clear. All right. So returning us to where we are in the here and now, the here now in space-time. 0, 0, 0, 0. Oh, that's a bit fiddly to get it exactly in the middle. Doesn't matter. That's where we are, or you are, right here, right now. Okay. So let us say, for shits and giggles, and for no other reason, there are two of me. Goodness, what a scary thought. Let's say I have an identical twin. Actually, the fact that it's a twin has no bearing on this argument. It makes no difference at all. It could be two completely unrelated individuals or two things. Doesn't matter. Let's just say they're two twins, just for fun. All right. Let's say my twin, my evil twin, let's say it's Yellow Ted. Perhaps he likes that idea. Okay, I can't repeat that, Yellow Ted. That's the sort of language we don't allow on this channel. Anyway, Yellow Ted is going to get into a rocket ship. Off you pop, Yellow Ted, and he's going to pop off out away from the Earth into deep space, and he's going to travel for me a distance of 1 light year. So there's the distance, 1 light year, in any direction. It doesn't matter, so long as the distance between here now and there, then, which is also now, is 1 light year exactly. Now, how is Yellow Ted going to get there without spending any time to get there? Impossible. Teleportation can't occur. No, Yellow Ted, you don't have magic powers. And again, that's the last warning on that kind of language, young man. Goodness, Professor Yellow Ted really is being naughty today, isn't he? Anywho, he's going to take some time to get there because he has mass and whatever. Luckily, his colleague, myself, I have designed for Yellow Ted a transportation methodology, a rocket ship, which can travel pretty jolly fast, shall we say. And let's say I'm able to get yellow Ted to half the speed of light, 50% the speed of light. A quick bit of math will tell us that that means to travel 1 light year distant from here, that will take 2 years of time as I perceive it to be. So the position now that yellow Ted is occupying is 1 light year distant from me, and he will arrive there in 2 years from now. So I will now move up to this point here, and he will be at that point there. We will both move through time. Okay, so let's put me back here on the Earth. Let's pop yellow Ted in that spot there. There he is. And we'll call that position A in space-time. Lovely. All right. Now, remember how I said that you don't move with respect to yourself? Of course you don't. You move through time as you perceive it to be only. Everything else moves around you. Now, remember I also said that the rate at which time flows past you is dependent on the rate at which you move through space with respect to somebody else. So, that being the case, what we actually have to do is move my vertical world line. And let's put another point here, point B. Point B is 2 years hence on my world line. Okay? With no movement with respect to myself, because how can I move with respect to me? Can't be done. Okay, so now what we have to do is move the verticality of the blue axis here such that that line now needs to intersect from the point that we both shared now, and it needs to go up through A. So let's do that, shall we? Now watch what happens to the squares, all the small squares, as I do this. Goodness me, they start to warp. Look at that. Anyways, let's get through to the point, which is about there. So we have now changed the point of view. We are now looking at a different frame of reference. We're now looking at Professor Yellow Ted's frame of reference. And what we can see there, let's just move that slightly because it's just slightly off where it should be. There it is, right on the mark. Okay. If you were to count forward in my frame of reference using my clock, which is CT, the black line here. So we go up vertically. How many squares up are 2 years? Well, 2 squares. 1, 2. 2 years have passed for me, sitting here on Earth, waiting and yearning for the return of Yellow Ted. Yellow Ted has zoomed off into space. 2 years have gone by for me. However, let's count how long in time has gone past for Yellow Ted in the same time. Wibbly and wobbly. Okay, so we start here and we count up 1 square, the slanted ones, and we count up to 2. Oh, not 2. Yellow Ted, by Yellow Ted's reckoning, has only been traveling for 1.7 years. Because Yellow Ted's clock is running more slowly than my clock is running. Now you might say, well, this is just theoretical. This is nonsense. Goodness me. Is there any practical proof that this happens? How can you squash time and make it run at different rates? Time is time, for goodness sake. And I've heard that many, many times. Well, yes, it has been practically demonstrated by a system called global positioning satellites. They fly around the Earth, zoomy, round and round and round. And your phone, this jolly thing that we're all behooving to, this mind vampire thing here, it sends out messages. Well, it doesn't send out. It receives messages from those global satellites that are beaming those beams of information back to the Earth, and it picks up 3 or more of those satellites, and it triangulates and says, this is where you are on the planet. It's brilliant. Except that what we worked out before we even sent the satellites up, so that's handy, is that we would have to adjust the clock reading in the satellite according to this Minkowski thing, because the satellites are zooming around the planet at a rate much faster than we're moving through space, because we're moving through space, but the satellite's going around the planet and through space, so that adds to it. It's moving faster than us. Its clock runs slower. If we didn't correct it, the GPS system would drift off by 200 miles every single day. So does it work? Yes. Is it a reality? Yes. So before anybody says, oh, this is theoretical, no, it isn't. Okay, good. So Yellow Ted has experienced 1.7 years of time. I have experienced 2 years of time. And we both would agree, if we could communicate instantaneously, which we can't, of course, that Yellow Ted has arrived 1 light year away from the planet to the predetermined point that we said that's where he's going to. Okay. Now, let's say for fun, Yellow Ted, having done that and got to that point, immediately turns around and returns back to the Earth at the same speed. Okay. Now, remember how I said I can't twist this graph back the other way because it won't allow it. So what we have to do is we have to be a little bit clever, and we have to say, well, the actual direction of travel, left and right here, makes no difference to this. It's only the magnitude of distance traveled. So if we continue on the same world line, instead of tilting the world line back the other way, as we should, we'll just continue it on as it is. And then what we'll do is we will place another marker here at point C. So now, if we put the equivalent point in time there, we'll call that D. So I have now waited yearnfully and sadly for the return of this rude professor, goodness me, for four long years, and he has returned unto me. Only here's the thing. Yellow Ted has not experienced 4 years of time to achieve it. He's only experienced 3.5 years. Half a year's gone missing between us. He has not aged as rapidly as I have. I've aged more than he has. Okay, fine. No problem, you might say. Until some clever people who really think they're clever, who really aren't as clever as they think they are, then go, well, this is a paradox then, isn't it? Because if we look again, shall we, at rule number 1, it says unto us. No, it doesn't say. It says icky. No, it doesn't say that either. It says there are no absolute frames. And no point of view has preference. And there is no right and wrong. If you also look at rule number 2, it says every observer has their own physical coordinates and their own clock. And they don't move with respect to themselves. So wouldn't it therefore be equally valid to say Yellow Ted has not moved because he hasn't with respect to yellow Ted. Me, bad bald man, and the planet Earth can equally be described as having moved away from yellow Ted, in the same way that we've just described yellow Ted moving away from the Earth and returning. Yellow Ted can say, I stayed right where I was. The Earth moved away from me and then came back. Therefore, I, Yellow Ted, Professor Yellow Ted, who's clever as I am, should have aged more than Bart and the Earth. So how is that possible? How can I be both younger and older? That's a dilly of a pickle, isn't it, boys and girls? Well, it's only a dilly of a pickle if you are the kind of student of physics who forgets relativity rule number 3. Here it is. If one observer wants to predict another observer's reality, the coordinate transformation is required. And that's what is being forgotten by these people who say, paradox, paradox. So let me show it to you. Here it is. Okay, let's look here at the diagram that we have set up. This is the one where I on Earth am looking at the orthogonal 90 degrees frame of reference, and Professor Yellow Ted is looking at the prime frame of reference, shown now by the blue lines and the slanty squares, which change both time and distance with respect to how I perceive them to be. Okay, so to swap back and then say, right, now let's imagine that Yellow Ted is the center of the universe and the Earth and I are now the prime frame of reference. We have to correct them back, don't we? Yes, we do. So the point A from the frame of reference of Yellow Ted having not moved with respect to Yellow Ted, is 1.7 years in time. So he's not moved, so therefore we have to put a marker about here, and then we have to adjust it until it says the correct number, which is 1.7 years of time. There it is. Slightly off the space axis, but that doesn't really matter so much at the moment. It's quite tricky to get it dead on. So E there should read 0.01.7. So point E is Yellow Ted's perception, and point A, in that case, has to be the Earth, doesn't it? Okay. Now then, let's do the same thing for point C, which is the point in time where the return back to Earth has occurred at point 0 in terms of the x-axis. And we will see that that's 3.5 years. So 1, 2, 3.5 years. Let's pop it about there and just sort it out until it's at the right point. 3.4, 3.5. There it is there. So F sits there. So C and F, A and E are the corrected conjugate pairs of events in time. Which means that both twins, himself and Professor Yellow Ted, actually agree. Yes, we do. We both believe that the person who was on Earth, whether the Earth moved or not, is the one who has aged more, and the one in the rocket, the Yellow Ted, has aged less, irrespective of this so-called false equivalence that has been thrown up as the paradox which disproves relativity. No, you forgot rule 3. Okay, there you go, boys and girls. That is the situation. So there is the twins paradox solved. All inside an hour, really. So what have we dealt with? We've dealt with Lorentz transformations. That was all the math that was on the left-hand side of the screen there, on which the Minkowski diagram is based. We've covered Minkowski spacetime as a parabolic architecture of space and time. Good. We've covered Einsteinian relativity 101, and we've solved the so-called twins paradox all in an afternoon. Hope you've enjoyed it. Tune in next time when we'll do something very similar, but probably quite different. See you then.